we had developed this generic control topology strategy where you had the plant, the estimator, you need to design the estimator gain G, one aspect in case you do not have all the sensors to sense all the states. You are doing full state feedback, let us say, and you need to sense all the states, and some may not be possible to sense. So, you put an estimator. You need to design the controller gain K. You need to design the reference generator. You need to design the steady state control input part. So, these things you have to, but before you do any of this, though this is our primary objective, you need to model the plant. So, the plant may be in any domain, it may be in the electrical domain, it may be in the electromechanical domain, magnetic domain, electromagnetic mechanical, hydraulic domain, electro-hydraulic, whatever, a mix. So, normally your plant's physical system is not going to be in a single domain, it will span multiple domains, and you should have a feel for it to model it, and whichever be the plant given to you, you should be able to have a model based on its physics of operation. So, generally models, if you see, there are two distinct categories. One is called system identification. Heard of this? So, other is called the physics based model. So, system identification generally goes in a kind of black box approach. So, it is a black box for you, a red box here in this case, and you have a set of inputs U and you have corresponding outputs Y. So, it could be a series of you keep on giving inputs, different inputs, and you will keep on sensing or reading out the outputs from that, and then based on this you will have a mapping and try to find out the input output relationship. So, this can be done online also, and most of the computer aided tools, they do system identification because it is easy for them to measure continuously input output, input output, input output corresponding, and based on that even the dynamic shape can also keep changing dynamically, and they will be able to understand what the plant is in that fashion. It is not coming from the physics of that one. This is more algebraic in the sense that it is like a lookup table. So, you have the U, you have the Y instantaneously. There is no time constant coming into the picture here, there is no time factor. So, for all that you have to go into the physics based modeling. So, that is what will give you more insight. You can study the dynamics also. We will try to do this type of modeling. This also later on we will be using when we are doing the estimators. Okay. When you are doing the optimal estimators, we will use this type of this one, but much later, because computer aided it is much more amenable to. This fellow is good for you to understand the system. It can give you a feeling of the time constant, order of the system, how many energy storage elements, where it gets stored, in what form, domains, losses, who are the dissipators, which components you may have to attack, design. See, once you do this type of only, it helps you in design, synthesizing this one. All those it is possible with this only. Cannot make a design out of this kind of thing. So, for the next few classes, maybe 2-3 classes, let us try to see if we are able to model a given system. Okay. So, for that there are many methods, and we will adopt energy flow method called the Bondgraph. Very famous actually in the mechanical and hydraulic engineering area, this Bondgraph, but not heard so much in the electrical engineering domain. Means it is there, people use, some people like us we use, but not very popular and not also taught in the syllabus of the undergraduate, right. It is not this one, but very, very powerful cross domain, across span. It could be many multiple domains your system may be existing in. So, this will be able to model pan all the domains. So, that is what we will be trying to look at. Okay. So, before we go into this Bondgraph method in detail, just want to take some feedback. Let us say you have a very simplistic system like this, a plant like this. Okay. How do you go, this is a what order system? This is a first order system. Why did you say it is a first order system?
One energy storage.
One energy storage. So, you have one energy storage element C, it is a first order system. How will we go about modeling this? Let us say, what is the model for this when I say? So, you identify first the number of energy storage as the first step. Identify the order, then identify state variable. What is the state variable in this case?
VC.
It is the voltage associated in this case with this potential storage element. The storage element is potential, and therefore, the potential variable will become the state variable, and therefore, in this case it is VC, which is the voltage across C. So, you will use, I will then say identify the input variables, and in this case it is Vi. So, you need to use only these variables, state variables, input variables, and the parameters like parameters of the system or the fixed parameters like the R1, R2, value of the components like this. It would in the mechanical domain it would be J, the inertial friction, B, those kind of parameters. Okay. You have to use only these variables and construct the model, because when you say a state equation, the entire system is actually determinable. You can understand everything about it just by the states and the inputs. Okay. So, in this case it is pretty simple, go directly to the energy storing element and look at its dynamic equation. Okay. So, you will formulate it in this fashion. So, C dVc by dt. So, C dVc by dt is the current that is flowing through that, which is this minus this. So, that is equal to V in minus V c by R 1, that is the current entering the node. Current leaving the node on the other side is V c by R 2. Note that I am not using any other variable other than the listed, and you should consciously make that effort. Can't just say V naught by R 2 or something like that one. All the variables that you will plan to use should only be in this list. Okay. Then only it will become causal. Later on I will come to causality issues. Then you know how to, from here, how to take it on further. So, let us say dVc by dt is equal to, so if you want to put it in the matrix form, you will put this and you have this is a first order system. Expressible in the standard state equation format. U is the input, this is the B matrix, this is the state vector, parameter matrix, and this of course is the differential of the state vector. So, everything can be reduced to this form called the state equation. So, that is basically what you would go about doing in the normal traditional method. The Bondgraph also will lead to this state equation of the system in a much more graphical way. So, let us try to understand what Bondgraph is and how we can get the state equation models out of that. So, it is actually a unified approach to modeling, this Bondgraph modeling. Before we go, we should understand why you want to do this approach, why you want to take this method. Let me start with a simple example, very simplistic example. You will get to know the problem that is associated with the traditional block diagram approach. This is a block. It has a gain of 0.5 input to its input to output, and we call it, let us say, G1 here. I will take another block, again 0.5, G2. So, you connect them in series and we say this is Vi and this is V naught. So, what is the transfer function? V naught by Vi, isn't it? So, what would you do in a traditional method? If I am having two blocks connected in series and say this is G1, G2, you will say V naught by Vi is G1, G2. So, if we do that, you get the equivalent, which is in this case 1 by 2 into 1 by 2, 0.25. Is this correct? Apparently it is so. In the case of the block diagram approach, this is what we would do, and not only that, you have a whole series of block diagram algebra. Now, let us say for example, I have this. So, let us say I call this one as G1, G2, G3. This is G1, G2. With feedback, you will say this is G1, G2 divided by like that. So, we are familiar with all those rules and block diagram algebra. Given a particular a set of sequentially aligned blocks, you will be able to reduce it into a single block. Now, look at this particular example and then see what happens in a practical system. Now, let us say I replace this block with a real system and a simple attenuator, let us say attenuator of 0.5 or R equal, and I have another attenuator, means that I will be connecting them together like this, and this is a series connection. Okay. So, this is Vi and this is V naught. What will be the voltage at this point? You will see that there is this R and R coming in parallel with this R, right. So, 2 R coming in parallel with this R, and it is actually not 0.5 times Vi. It is R in parallel with 2 R divided by R plus R in parallel with 2 R, right. So, at this point it will be 0.4 Vi, not actually 0.5 Vi. And then this is, now if I take from here to here, there is a reduction of 0.5, 0.2 Vi. So, because of this loading effect in a real system, what you actually would get is 0.2. Of course, for this another system it will be another number, different values of these R's, different number. So, but we will always do our designs with this, assuming that the input impedance is infinite, output impedance is 0. So, that is one very serious assumption that we make, and all our block diagram algebra that you do for your modeling will become invalid. So, you will assume that Ra is infinite, R naught is 0, and you will do all your calculation in this fashion, but actually there will be quite a large mismatch between these two, and this is a very simplistic example. Imagine much more complex dynamic situations, you will land up in some serious problem. So, I will say that Bondgraph is something that will alleviate this problem. Okay. It takes care of loading effect. Okay. It is not just only signal flow like in block diagrams, it is also considering power flow. So, at the last stage, final stage, if there is a loading effect, it will go to the next previous stage, so on up to the first stage, source stage, it will percolate down, and the first stage you will see an increase in current or increase in power that is felt. But in the case of the block diagram, you can load the last stage to whatever extent you want, but it will never percolate to the first stage, basically because it always thinks that the next stage is having infinite input impedance. So, you will not see an increase in power. So, you will see that there is this dichotomy, you will have this problem of not trying to meet the conservation of energy, because it is just only signal flow, it is not taking two variable thing like power flow or the energy flow. So, that is one main issue. The loading effect, as I said, is automatically inherently taken without thinking, you do not need to think about that. Let us say there is one system, one person is designing, another system someone else is designing. You take these two models and then concatenate, you will automatically see the loading effect percolating from this to this. Then you can keep on cascading and concatenating models done by different people. Let us say someone in the mechanical domain has done a model, someone in the electrical domain has done a model, someone in the magnetic domain has done a model, but you need all these three in cascade. So, you will take the electrical, magnetic and the mechanical models, cascade them, automatically the loading effect percolates to the source side. So, if you change the load in the mechanical domain, you increase the load torque, it will go into the magnetic domain, percolates, you will see the change in the flux, and that will get percolated down into the source side, which is the electrical side. You will see a change in the power flow from the source. All this happens inherently without you having to really take care of that consciously. So, this is a very important benefit that you would get, and more closer to reality, more closer to your practical system. The output of the bond graph, the deliverable of the effort that you put in modeling with this bond graph is a state equation. It will give you a set of linear differential equations, first order, and from there you will be able to put forth the state equation of the entire system by inspection. That is the important thing. You do not need to do very large derivations. Just by inspection you should be able to read out, with practice you should be able to read out the state equations looking at the bond graph picture. Okay. Then, as I told you, the physical system spans across, could be hydraulic, could be electro, could be electromechanical, all across these, and then you should be not feeling out of place modeling something in the mechanical domain. You should not be feeling out of place modeling something in the hydraulic domain. Everything should fall in place, and the one common connecting item which connects all these domains is energy. So, the energy flow is invariant in all these domains, and therefore, bond graph being an energy based approach to modeling, you will not feel out of place whichever be the energy domain that you will be modeling. Then the fifth and one of the most important points is causality. What is this? This, you have an equation, right? If I am having R, Ohm's law, I have V and I have I. I have here written two equations, V is equal to I into R and I is equal to V by R. Are there two different equations? They are one and the same, right? It is just algebraically I have placed the things, but in the physical sense it has a, pardon me?
Second one is causal.
Both are, depends upon the situation. At different places I will be the cause and V will be the effect. in which case I have to use this equation, and some cases V will be the cause and I will be the effect, in which case I have to use this equation. So, Bondgraph inherently has this causality into the picture. Automatically which constitutive equation that has to be used will get addressed at the time of designing or modeling with the help of Bondgraphs, which is not, causality is something that we do not actually talk of in block diagram approach itself. See, for example, if I take a source, I will say I will take a voltage source, what is the cause and effect for this? In this case, the source defines the voltage. Okay. So, this terminal, the voltage is defined by the source, fixed, the voltage source. What about the current flowing here? It is decided by someone else, it is decided by something else, whatever may be connected here. Say I have this R1. Now, how would we model this? If I connect it, what is the model for this? Very difficult, right? We do not have an energy storage material, and the closest model that we have written is, if this is V I and let us say this is V naught, V I minus V naught by R1 will be the current that is flowing through this into this is R1 and R2 into R2 will be V naught. Now, if you look, this is actually a causal relationship where we have the V naught, the present value of V naught determined by something which is also having the present value, present determined by the present, right. So, you can say it is a causal in the sense that this cannot happen. Can it happen? Present output is dependent upon the present output to determine that. The present output should not be dependent upon itself, but all past values no problem, previous history no problem, but it cannot be dependent upon the present or the future. But for convenience we would write this as V I right, and then say okay, V naught is equal to this divided by this, dependent on V I. But actually that is actually a very false notion, in the sense that very specifically for that very particular value of R2, looks as though that V I is determining voltage and also current. V I can't, the source, a voltage source can't determine both, it can determine only one. So, by this you will say that such a thing cannot exist. You need to have some dynamics coming to picture. So, there will be in a natural system something here which will make it a possible attenuator. In ideal what you will call the sense where it is an algebraic, in an algebraic sense where you do not have the dynamics, it cannot happen, because present has to be dependent on present. So, there will, if it works, then there is some dynamics involved, there is some capacitance coming into the picture. Now, these causality issues.
Sir, could you please explain why we are not taking the second one? Why are we taking the first one to be that equation? Since
Why you are not taking, okay, see, in this case, what is V naught? Vi, if I solve this, into R2, right. So, this is the current that is flowing here, this is the current that is flowing here, I. Okay. So, by this it appears as though the current is also decided by this, but remember that source can decide only one thing, voltage alone. If it is a current source, it can decide only one thing, current alone. The effect of all the other circuits put together should decide the current. Okay. This is an algebraic manipulation, but what is actually the model should be this. This potential minus this potential divided by this will give you the current, flowing through this should give you the potential at the output, which will give you the present output dependent upon itself. So, that becomes an algebraic situation, it is an algebraic system, an algebraic system cannot exist, just like a differentiator also cannot exist, right. Can it exist, differentiator? In a practical system, all our models we have d by dt, right, we have dx by dt is equal to, okay, this is again for convenience, ax plus bu. So, what would be dx by dt? Slope, okay, slope of x, fine. So, you have something like that, and then you have, let us say I want to find the slope at this point in time t, this is t. How would you go about doing it? So, you actually take neighborhood of the operating point or the neighborhood of that point, in this case this is t, x axis is t, not u, remember that. So, neighborhood of the operating point, you will take this point, slope, I will get slope at this point, but I do not know this is a future point, right. So, that is not possible, again not causal, therefore, I cannot take future, the best I can take is this, right. If I make this bigger like that. So, let us say I have a point here and a point somewhere downstream, this you can calculate, but I can get the past point, this is past, this is present, this is now, this is past, this is future, right. So, corresponding to this now, getting this is possible, but I cannot get this. So, what is the next best thing I can do? I can do that, but you will not get slope at this point, you will get the slope at this point, which is not what I actually want. You will actually get the slope of a bit past. value, never of now, and therefore you cannot have d something by dt. It is not possible. Then you can predict the future if it is possible. So, d by dt cannot exist at all, at least in this known universe that we know. We cannot have this. It is in the limit as that thing goes towards. How do you define this? In the limit as delta t tends to 0, which means as that tends towards now. But always you are talking of some point future t0 plus. T0 plus cannot be there, right. So, you can never have it, and therefore, it is not possible, and therefore, it does not exist, and therefore, any system which says d by dt cannot exist, and therefore, it is not permitted. Get the point? It is an a-causal system. So, what is preferred by nature is integral. This is alone preferred by nature, allowed by nature, can exist. All your simulation algorithm will work only with a nice integral algorithm in place, numerical integral algorithm in place. The system, if you have to simulate it or if it has to exist, it is the integral accumulator which will actually make it work and make it possible. So, this possible thing. So, nature prefers integral over differential, but we can always express it in your state space form. You can like we shifted algebraically the variables to the left and the right, no? You can always shift the variables to the left and right and express an integral as a d by dt and things. That is for our operational convenience. Okay. So, what is the principle that we will follow for modeling? See, when you do energy based modeling, there are not many things that happens. See, I will take a source, simple. So, this is a source, and what energy has to do? It emanates from a source, and so one reaches some place, right. So, it has to reach a destination. So, you have a source which is giving out energy, energy flows from there to the destination, and in between, when energy goes from one place to another, A to B, source to destination, some things happen. What are the things that can happen? One, it can dissipate, means someone else can draw few packets of energy somewhere else and then it actually does not reach the destination, dissipate. It can store for some time and then get released, okay. And storage can be of two possible forms only, okay. One possible form is potential storage, another possible form is kinetic storage. So, apart from these three effects, what else can happen? It can get transformed. So, it can get transformed from one domain form to another domain form. It can get transformed from mechanical form to electrical form, or from electrical form to magnetic form, or to a hydraulic form. So, there can be a transformation that can occur. These are all that can happen when energy moves from one place to another, okay. Nothing more than this can happen. So, this is actually what we will be trying to model. So, when energy is flowing, when power is flowing, we will see where it can dissipate and where it can store, or can it store at all, and this in fact will give you the clue for putting in the variables. This along with causality. The moment I know that I am having an a-causal thing, I know it cannot be, and therefore, you will start adding in non-idealities like a capacitance across a junction, capacitance across a typical textbook attenuator of resistance by resistance which cannot exist. These kind of things you will start adding, knowing that okay, this is how the energy can flow. So, in the electrical domain we call dissipate in something called R, a resistor. In the mechanical domain will be dissipate in something called B, friction. like that each domain will have its this one, but we will use for our modeling, because we are all electrical engineers, we use electrical symbols. But remember that the electrical symbols that we are using are generic. It does not mean or does not only stand for the effect in the electrical domain, but we are saying that it will stand for that effect in all domains. Okay. A mechanical engineer will use symbols which he is comfortable with, but for us we are more familiar with, for dissipation R we will use R. For kinetic storage, half Li square L is what we will use. Potential storage C, half CV square. Okay. In each of the other domains it will mean inertia, compliance, all those things, but anybody can convert it into accordingly. There are transformations across domains, GY gyrator. Okay. Most of the transformation across domains happens with the gyrator. Transformation within the same domain happens most of the time with TF, transformer. We will call it as a transformer. Transformer here is a generic transformer. I will explain what is a generic transformer. Electrical transformer is a special case of the generic transformer. So, some symbols and notations what we will follow, okay, for modeling step by step. So, I will be using this, and in fact all the literature also uses this half arrow. I have shown this half solid arrow, but when you are writing in the notebook we can use something like this, half arrow. Half arrow implies an energy bond or a power bond. Okay. Now, each of this bond is associated with two variables. One is a potential variable and the other one is a flow variable. Okay. So, it is associated with two variables, and in the electrical domain, a potential variable means voltage, EMF. A flow variable would mean current, but I will use the more generic term. Potential is called effort and the current flow variable is called flow in a more general sense. Okay. So, we will have a flow variable and effort variable associated with every bond in the graph, in the bond graph. So, one bond means it will have these two variables of that particular domain, whichever domain it is, and sometimes we do not put these variables explicitly, we do not write it, but it is there. Even if we do not write it, it is there by it may be understood what it is, and you do not need to explicitly write it and clutter up the page. Okay. And what is the direction of this arrow implying? Direction of the arrow is nothing but direction of the energy flow, not the direction of the power flow. Be very careful, distinguish this. It is not the direction of the power flow, it is the direction of the energy flow. Power flow can be bidirectional at any given instant of time. When I take a source to the destination, in between you could see the power flowing left to right, and sometimes it can flow right to left, but overall the energy may be going from left to right. So, it is the energy flow, accumulated energy flow, that direction is what this is indicating, because instant by instant power flow can be in any direction, which we will not know what is happening at a given point in time. Okay. So, this is the notation that we will use for each bond, and always every bond, its product of the two variables is always power. So, which means that is a clue for us to choose appropriate variables in any given domain. Always the product of the two variables that we are talking of, one potential and one flow variable, effort and flow variable is always power. Okay. Just some examples and then I will leave you. So, we have this, let us say, typical bond graph, and let us see some domains. Okay. I will say, I will have the chart like this. This is the domain. What is the effort variable, what is the flow variable, and what is the product power. The power product has to be always power. Electrical, see electrical we know what is the effort variable, voltage. So, E is voltage, F flow variable is current, and the product E into I is power always. Another example, mechanical, linear, effort is force, flow is velocity, force into velocity, power. Mechanical, rotational, what is effort and what is flow. So, in the rotational you have the torque as the effort and the angular velocity. So, you have the torque T, see the angular speed, oh it should be omega, okay, the symbol has not come properly. Normally we use omega. So, if I am having torque and omega. So, this is the where the power is T omega. Okay. Hydraulic, effort is pressure difference, pressure head. In some cases they will use head. Head is actually related to pressure. So, pressure is the variable and the flow is flow rate or discharge rate. Discharge is Q, discharge volume, discharge rate of discharge, dQ by dt. So, used in all these pumping applications, water pumping or any other pumping applications. Pressure into dQ by dt is power again. So, if you know one variable, you can find out the other variable knowing the power relationship. Hydraulic, you could check magnetic. In the magnetic, what is effort? MMF, as we know, MMF or Ni, and the flow is rate of change of flux. Remember, because it is MMF into d phi by dt, I put df by dt here, d phi by dt will give you power, right. Thermal, temperature is the effort, flow is entropy rate. Entropy is power flow or heat flow. Per degree per unit temperature. So, entropy is actually the energy flow or the heat flow in a medium per unit temperature of the cold body. So, d by dt entropy is going to give you a power unit. So, entropy rate and into temperature will be power. But thermal domain is slightly different. It is the parent domain. The parent domain means in the terms of energy, always energy will flow, finally it will reach the thermal domain, always. And entire universe also tends like that. Finally, it will be all dead heat. Okay. So, the interesting aspect in the thermal domain is that there is no dissipation there. When we say energy goes from A to B, there is no dissipation in the thermal domain, right? By logic, it should not be. Can you have dissipation in the thermal domain? Where will it go? Where will that loss go? As all losses go as heat. In the thermal domain, where will dissipation go? It has to be in the second domain, right? So, there it is generator. Any heat from all the other sources, it goes as heat, means for the thermal domain it is a source, right? And then there is no loss within the thermal domain because it stays there. It cannot come out of that domain. So, it gets locked there. So, that is a very, very unique domain, is the parent domain, which is the least work potential. Finally, it goes and settles there entire. So, like that. Okay. So, this is this will give you an idea of what we would mean by this flow and effort. Okay. So, next class we will continue with this. We keep remembering these symbols. We will use these symbols to model physical systems, and we will see how the modeling concept evolves. Okay. Finally, we have to get the state equation by inspection.